Okay, welcome to Let's Get to the Marks. I'm going through the AQA GCSE Combined Science Trilogy paper. This is the chemistry paper two, so it's the second exam for chemistry. It's an hour and 15 minutes. It's 6 questions. This is worth doing if you're a triple scientist because it also covers sort of 70% of the content you'll be doing in your paper two. So it's definitely worth doing all of the combined science papers as well. Okay, as always, when I go through the questions, I suggest that you pause the video at the start, grab a pen, grab paper, write your answer down, make the revision active. It helps activate the brain and it's much more effective revision than passive revision. Or if you haven't got a pen and paper, you can just answer it in your head, try and read through and have a go at the questions first, then unpause and watch my explanation. All right, let's get into it. So, question one, alkanes and alkenes are hydrocarbons. Define the term hydrocarbon. This is where you should pause the video. All right, I'm going to go through the answer. So, what is a hydrocarbon? A substance, a molecule, a compound. I'm going to call it a compound, but substance, molecule, or compound would be good. Or chemical, you could even say that contains hydrogen and carbon atoms only. Now, sometimes these are 1 mark. In the past, they used to be 2 marks, and they would stress that you had to say only hydrogen and carbon. Now they probably allow you to just say a substance that contains hydrogen and carbon, but it should be hydrogen and carbon only. Okay, there we go. If you contain hydrogen, carbon, and oxygen, like a glucose molecule, you are not a hydrocarbon. Right, let's move on to the next question. 1.2. The general formula for alkanes is CnH2n plus 2. Determine the formula of the alkane with 10 carbon atoms. Go on, pause the video, see if you can write out a formula for an alkane with 10 carbon atoms. All right, I'm going to go through it. So we've got to just follow this formula. And by the way, you have to know this off by heart. You could well be asked this for 1 mark. So if N is 10, so C10, what would H be? Well, you're going to go 2 times 10 plus 2. So you can see that H is going to be 2 times 10 is 20 plus 2, 22. And that is going to get you a mark. Check out that too. Seriously dodgy. All right, let's move down. Right, we're on to 1.3. Crude oil is a mixture of hydrocarbons. Figure 1 represents industrial equipment used to separate crude oil into fractions. Here's figure 1. It shows us that there's a temperature gradient because we go from the bottom where it's hotter and you can see this arrow's going up, decreasing temperature. And then we've got a pipe going in to this equipment and an arrow going up. I guess that says heat. Yep, heat at the bottom. And there we go. And then we've got various pipes coming off at different sections of this column or tower. Explain how crude oil is separated into fractions, 4 marks. I'm going to come up and rather than write it on the lines, I'm going to write my answer up here. So what I suggest, 4 marks, how do they separate crude oil into the different fractions? You need to know this off by heart. Go for it. Pause the video, have a go. All right, I'm going to go through the answers now. So hopefully you've had your go. The first mark is to say the crude oil is heated. Look here. This is the first step. So we're going to say, need a capital. Crude oil is heated. Now, sometimes sheeted, oh my gosh, I hope not, is heated. And I'm going to put this word because I love this word and vaporized. That means turned into a gas. You could say evaporated. Okay. Crude oil is heated and evaporated or and vaporized. Now that's going to get me my first mark. What happens next? So the crude oil comes in here as a gas. It then rises up the tower. So I'm just going to put that there, crude, but this won't necessarily get you a mark. Crude oil vapors rise up the tower. It's actually split into something called fractions, which are different sized hydrocarbons. So the crude oil vapors or fractions rise up the tower. What I want to say is what happens to them? Well, we need to mention this bit, the decreasing temperature. So there's a 3 mark. The tower, you can call this a column. The tower has a temperature gradient. Now, you might not be able to remember that term. Okay, that's a fantastic term to remember. You can just say it is hotter at the bottom and cooler or colder at the top. And either of those is going to get you a mark. You're explaining that it's not all the same temperature. So it's hotter here than it is up here. So that is what we want to talk about. What happens as the fractions move up the tower? Well, they turn back into a liquid from a gas. Do you remember the key word for that? So we want to say um, the different fractions condense. Oh my gosh, condense at different parts of the tower. So that is another mark to say, well, different ones come out. For instance, kerosene comes out before petrol. So why do they come out at different parts of the tower? Or bitumen comes out at the bottom here, and I don't know, heavy fuel oil comes out here. So why do they come out at different points? Well, it's because the different fractions have different boiling points. The different fractions have different boiling points. Boiling points is the point where you either boil or condense. So the fact that they have different condensing points or boiling points, and the fact that the tower is hot at the bottom and cold at the top, means that the tower has different temperatures throughout it. That means that the fractions are going to turn back from a vapor into a liquid at different parts of the tower. So we're working our way across by saying the crude oil is vaporized into a gas. The gases rise up the tower. It's at different temperatures. So the different fractions will condense at different parts of the tower and come off as liquid. And the reason is because they each have a different range of boiling points or different boiling points. Coolio, that's your 4 marks. How did you do? I would make sure you put that on a revision card if you don't know that now. This is quite a common content question to be asked about. Sometimes this is quite nice and straightforward. They just said, how's crude oil separated into fractions? Sometimes they'll put a little bit of context into it and they'll be like, explain why petrol um, is separated higher up the tower than kerosene. And it's the exact same answer. They've just used some of the names of different fractions, but you would say the exact same 4 mark answer. So it comes up quite a lot, that. Right, 1.4, the alkane molecule C14H30 can be cracked to produce smaller molecules. Balance the equation for the reactions. So cracking is where we take long chain hydrocarbons, saturated alkanes, and we split them to make smaller alkenes and alkanes, or smaller alkanes and alkenes. Now we can see they've left a space here, so we need a number here to balance this all up. We've got C14H30, so why don't you pause, have a go, see if you can come up with which number should go in front of this. Well, I've got C8H18, so I want to take that away from that. So I want to minus that. And if I take 8 from 14, that leaves me with C6. And if I take 18 from 30, that leaves me with H12. And as you can see, how many of these am I going to need to make C6H12? Well, I'm going to need 2. So that balances it. Now I go 6 plus 8 is 14. And then I go 2 times 6 is 12. 12 plus 18 there equals 30. So that's really like an equal sign, and you just want to make sure that it's even on both sides. That is a mark. Keep on moving. Propene C3H6 is an alkene. 1.5. Describe the test for alkenes. 2 marks. Give the result. So alkenes, you might be thinking, what is an alkene? An alkene is a molecule that has a CC double bond, and of course it ends in ENE. Describe the test for alkenes. Well, when we add bromine molecules, or we add bromine across, what happens is the double bond disappears. Now, bromine is orange in color, but when it joins onto an alkene, we get a colorless solution. So the test is add bromine, but it's better to say add bromine water. It's a safer version of bromine. Bromine is a very volatile red liquid that's acidic and is quite dangerous. It's vapors, but we dilute it with water and it goes orange in color. And the result is it goes orange to colorless. You probably just need to say it goes colorless. You don't need to mention that it's orange first, but I'm going to put that there. 2 marks. Let's go. 1.6, Polypropene is made from propene. Polypropene is made from propene. Figure 2 represents the repeating unit of polypropene. Here we go. What type of substance is polypropene? So what do we call, what's the general name for things like polyethylene, polypropene, polybutene? They're known as polymers. Many monomers joined together. You could give them their common name, plastics. And there we go. Let's give it a mark. Let's move on. Don't forget to pause the video at the start of each and have a go. We're already on to question 2. So, some factors affect rates of chemical reactions. 2.1, a student investigated the effect of changing the particle size of calcium carbonate on the rate of reaction with hydrochloric acid. Figure 3 shows the apparatus. So if we study this apparatus, we've got lumps of calcium carbonate here. We've got hydrochloric acid. We've got bubbles coming up. We've got a conical flask shaped like a cone. We've got a stopper or bung. We have the delivery tube, which can be plastic or glass. That's coming down here into a trough of water. And then we have a measuring cylinder, which has been turned upside down and obviously filled with water. We have carbon dioxide coming up here, and we have the measuring cylinder we already mentioned. Let's get on to the question. What? It's a 6 marker, folks. Describe a method the student could use to produce valid results. Now, if you're just asked a vague question like this, like just plan out a practical. Okay, if you're asked to plan out a practical like this, sorry, I just have to pause while I my throat. Uh, there are 3 main things when you're describing a practical. If it's open-ended like this and it's not specific, it's just plan a practical, how you do this to take valid results, then there are 3 main things you want to break your marks down into, and they are the independent variable, the dependent variable, and the control variables. Now, what I suggest is that you have a look at what they're doing here. You decide what is going to be your independent variable, dependent variable, and control variables. You make a list of that. Pause the video, have a go on a bit of paper now, see if you can work out what the independent, dependent, and the control variables are, and then I'll go through the answer. Okay, right, I'm going to go through the answer now. So obviously what they're doing here, that investigated the effect of changing the particle size. So that is our independent variable. Why is it independent? The experiment doesn't change the particle size. The scientists do. It's independent of the experiment. It's down to the scientists or the people doing it. They are changing the particle size on the rate of reaction of hydrochloric acid. So what are they actually measuring? Well, we've got a measuring cylinder. There's a clue. What do you think we're measuring? Well, we're measuring the bubbles of gas. We're actually measuring the volume. So our dependent variable is to measure the volume of gas. And then what things do we need to keep the same? Well, if we're changing the size of the calcium carbonate, what should we keep the same? You've got to think, what affects the rate of reaction? What factors do you know that affects the rate of reaction? And that is temperature. You've got pressure. We don't need to worry about pressure here because we're dealing with liquids and not gases, really. Where our reactants aren't gases, it's a liquid and a solid. So we've got, we're changing the surface area by the particle size, but we want to keep the temperature the same and the concentration of things the same because they will affect the rates of reaction. And that's really what you need to talk about. I'm going to put this together in a 6 marker. So let's zing down to the, oh my gosh, I can't even operate the mouse. Let's zing down and I'll put this together. Describe a method the student could use to produce valid results. So I'm going to basically say use 5 different sizes of calcium carbonate. Okay, so we're going to use 5 different sizes of calcium carbonate. Weigh out the first sized particles to 5 grams. So we're going to use 5 grams each time. Keep the mass the same each time. So I want to use 5 grams each time. You could use 10, you could use 1 gram, you can say any mass, or you can just say keep the mass the same each time, use a balance to measure it. We could say, that's a bit extra, but I'm just going to put that in. Use a balance to measure mass. We could say something like, don't forget to zero it first, means set the balance to zero, but I'm not going to bother because I'll run out of room. So that is my independent variable ticked off, right? And I've mentioned my independent variable. I've said at least 5 different ones I'm going to change it to. Now I need to mention my dependent variable, but there's a few things before that. I'm going to say place calcium carbonate in conical flask. I'm not going to get a mass for saying place in conical flask. It's the next bit, which is one of my control variables I'm going to hit up. So add, and I'm going to give a volume 5 centimeter cubed, or you could just say the same volume. So you could say the same volume each time. Now it doesn't have to be 5 because I've used 5 grams there. So I'm going to change that and make it 10 centimeters, or actually I'm going to say 15, just so you don't get confused and think I'm trying to keep everything to 5. You don't have to state a number. You can do if you want. I'm going to say the same volume each time. So add 15 centimeters of hydrochloric acid, right? I could say measure with a measuring cylinder. I'm not going to bother, but you could put that. So add 15 centimeters of hydrochloric acid of the same concentration. Now I could say 0.5 moles if I want to give it a number, but of the same concentration each time. So again, this is control variables. I'm controlling the volume and the concentration. So I've mentioned a couple of control variables there. And then I'm going to say quickly put the stopper and delivery tube in. Why am I saying quickly put the stopper and delivery tube in? Now notice this word here, describe and valid. Valid means you've talked about control variables. So that's what valid means. And describe means just say what you need to do. Don't explain. If it said describe and explain a method, I'd say quickly put the stopper in the delivery tube to prevent the loss of gases. But that's explaining why I'm putting it in quickly. I don't need to explain it. It says describe. So quickly put the stopper and delivery tube in flask. Then what do I need to do next? Let's say every minute, or no, I'm going to say every 10 seconds, record the volume of gas given off in the measuring cylinder. Keep eyes at eye level. Did it say ignore safety? I'm going to say wear goggles. Again, I don't need to explain why. I'm just putting that as my safety measurement, safety thing to wear goggles. They might not give you a mark for that. They might ignore safety. But essentially, every 10 seconds, I'm recording the volume of gas. This is my dependent variable. I've explained what I'm doing. This is how I'm going to measure the rate of reaction. So, and that's what I need to do until the reaction stops, or I could say for 5 minutes or for 3 minutes. So every 10 seconds, record the volume of gas given off, and I'm going to do that for 3 minutes. Now I'm going to record my results, and then I'm going to repeat this 2 more times and calculate the average rate of reaction. Now, you might not have to talk about this. They just like the word repeat. So I'm going to say repeat 2 more times. We might say remove anomalies and calculate the mean or average rate of reaction by, I'm putting how to do it. You probably don't need to put this, by dividing centimeter cubed by time. So what I can do is find out how many centimeter cubed are given off every second. Okay. What else? What else? What else? What else? I'm going to say repeat again 3 times at each different particle size. Now, one thing I did miss out in my control variable over here, I didn't mention temperature. So I'm going to say keep, because that is a big factor that affects the rate of reaction. Keep the temperature the same using a water bath. Okay, water bath in all biology, physics, and chemistry is how you keep temperature the same. And actually get me 6 fat marks. Okay, so there we go. Lovely jubbly. Right, let's move on. That was long. Right, 2.2. The student investigated the effect of increasing the temperature on the rate of reaction. Explain the effect of increasing the temperature on the rate of reaction. Refer to particles and collisions in your answer. So they've given us 2 hints. We need to talk about particles and collisions. It's going to be 2 out of 3 marks. And look, we're not using the word describe. We're using the word explain the effect of increasing temperature on the rate of reaction. If I increase the temperature, what will happen to the rate of reaction? The first mark is a description. And then the explanation must contain particles and collisions. So I'm going to give you the first mark. It's just a description, even though it says explain. So we're going to say increasing temperature increases rate of reaction. So that's the obvious thing, but that's actually a description rather than an explain. But you're always going to put that. And now we need to say why. Why does the temperature increase the rate of reaction? And we need to talk about particles and collisions. So we're going to go with uh, more kinetic. Basically, the higher the temperature, the more kinetic energy. Particles have more kinetic energy. I'm going to start like that, actually. So particles have more kinetic energy. So I've mentioned the word particles. This means they move faster. Now, is that 2 marks? No, that's just 1 mark. So I could just say they move faster. Particles move faster, or I could say have more kinetic energy. But I've said both. You only need to say one of these, but I like to put both just in case, whatever. And the third mark is going to be for using the word collisions, but there's another word we need to use with that, or they won't give you the mark, and it's called frequency. So this means more frequent. I'm going to put successful as well, collisions. And there we go. You cannot have a reaction unless there is a collision. And more frequent means you get more collisions every second. Or you can say more frequent collisions. So you can either say more frequent collisions or more collisions per second. And successful means that that collision results in a reaction. And why is it successful? Because it has more energy. Anywho, that's your 3 marks. Let's move on. So do remember that when you're going to write the word collisions, you write frequent. Catalysts affect the rate of reaction. What is meant by a catalyst? So they haven't told us what it does to the rate of reaction. So one of the marks here is to say what it does to the rate of reaction. Does a catalyst increase the rate of reaction or decrease the rate of reaction? Does it speed up a reaction or slow it down? So I'm going to put it in simple terms. Catalysts speed up reaction rate. Now, I could say they, increase the reaction rate, but they speed up reactions. Okay. And how do they do this? They do this by lowering the activation energy. So they do this by lowering the activation energy. And they provide an alternative route. But also, I want to say they do not get used up in the reaction. So I'm covering all bases here. I'm not sure what the 2 marks are. One of the marks is going to be they speed up the rate of reaction or they increase the rate of reaction, but I'm not sure whether they want explain, because they haven't said explain how a catalyst works. That would be by lowering the activation energy. But another key thing about catalysts is they don't get used up. I have a feeling it's this one and this one. They speed up the rate of reaction without getting used up. The explanation for how they work is they lower the activation energy, but I am putting all 3 to cover my bases. I suggest you do the same. Okay, let's go on. What are catalysts in biological systems called? So why don't you pause the video and try and think of what are the only catalysts you know about in your biology? And hopefully you come up with the word. It's enzymes. And that will get you a mark. Remember, enzymes speed up reactions without getting used up, but enzymes can be denatured at high temperatures. That's the thing in biological systems. They don't like to get too hot. If you're using chemical catalysts, inorganic, non-living, or made of non-organic material, like inorganic catalysts like nickel, platinum, or iron, you can heat them up to 450 degrees. They are not going to denature. They're not made of proteins with specific 3D structures. Right, we're on question three. Three, here's the magic number. Some fractions of crude, no more, no less. All right, some fractions of crude oil are processed to produce fuel for transport. Describe how crude oil was formed. So nothing to do with this. They're processed to produce fuel for transport. This is just a throwaway line to give you some context. Describe how crude oil is formed. Four fat marks. Okay, so there's some key stuff here. They don't often ask this question, but it's a good one that they do because it is on the syllabus and it's nice to have some examples to go through this. Grab your pen and paper. This is just a pure content recall and it's a description, not an explanation. So just describe how is crude oil made. We want four keywords. Go for it. All right, I'm going to go through the answers now. So you can have a little look. And if you don't know any of these, that's a great one for a revision card. Right, describe how crude oil was formed. And then on the back of the card, put these 4 points. So we need to know that it happened over millions of years. So we've got to get that in. And then what is it formed from? So we want to say formed from, what is it made from? Dead organisms. Now, specifically, dead marine organisms. Now, that doesn't mean, "Huh, we're in the marine, soldier." No, it doesn't mean that it's a soldier. Marine actually means the sea. Marines are soldiers that fight in the sea, but marine just means the sea. So it's made from dead marine organisms. And you might be someone who says, "Sir, will I get a mark for saying plankton?" Yep, that's absolutely cool. That's a marine organism, an organism that lived in the sea millions of years ago and lives in the sea today. Phytoplankton, all sorts of things. But you can just say dead organisms, but specifically dead sea organisms. Okay. And you don't spell formed like this. Fomred. Yeah, it's not from red, it's formed. Okay, formed from dead organisms, plankton. And that's a first mark. Now, the second point you need to have put somewhere in your answer, millions, not thousands, millions of years ago. It's actually hundreds of millions of years ago. But if they see the word a long time ago or millions of years ago, they're going to give you the mark. They won't give you the mark for thousands of years ago because it's a real long time ago. Okay, so that's 2 out of our 4 marks. Now, we've got the idea that there were these dead organisms millions of years ago. Now, they partially decayed. I don't know if they'll give you the mark for this. They partially decayed in anaerobic conditions. What the hell does that mean? There wasn't a lot of oxygen about when they were formed, so they decayed in a very special way. Now, I'm not sure that's going to be on the mark scheme, but they are going to have under very high heat and pressure. So I think the remaining 2 marks are going to be about heat and pressure, but you might get a mark for decayed in anaerobic conditions. I'd have to check the mark scheme, folks. But this is the kind of thing I would want to put in my revision card. So they're made from dead sea organisms or marine organisms millions of years ago that were trapped under rock. And so no oxygen. We can just say they partially decayed in anaerobic conditions, or we don't even have to say partially. We can just say decayed in anaerobic conditions without oxygen under very high heat and pressure because they're underneath loads of rock. So it's hot and high pressure. Boom, 4 marks. Right, let's go down. Transport is a source of atmospheric pollution. Suggest how sulfur dioxide can be produced by transport. Right, let's look at this name. How is sulfur dioxide produced by transport? What do we mean by transport? We mean cars, lorries, planes, that type of thing. So suggest how is sulfur dioxide produced by cars and things and transport vehicles? 2 marks. So why don't you pause the video and have a go? Okay, I'm going to go through the answer. Right, fuels contain sulfur impurities. Okay, so there is sulfur in fuels. What does that join with? When we burn the fuels, burning the fuels combines sulfur with oxygen from the air to make sulfur dioxide. So there's oxygen in the air, sulfur's from the fuel. They join together, and that is your two marks. So we've got sulfur in the air, sulfur in the fuel, oxygen in the air. When we burn, they form SO2. So sulfur, the fuels contain sulfur, and they join with oxygen from the air. Those are the two marks. You could just write fuels have sulfur, oxygen joins with it from the air, and you get two lovely marks. Right, let's move on. Moving on. 3.3, give two problems. I better not stop singing. I didn't even, yeah, anyway. My art and singing are just that music and art, I did bad in both. Like the subjects though. Give two problems caused by sulfur dioxide as an atmospheric pollutant. So what are two problems caused by sulfur dioxide? Ooh. It's a little bit hard. Hopefully you all know this one. Sulfur dioxide goes up into the air and now I'm not 100% sure again without checking the mark scheme, so I'm going to do my smash approach. So sulfur dioxide can cause acid rain. And what does acid rain do? Acid rain kills fish, kills trees, changes the pH of soil. So, but do they mean that acid rain is one of the things, or can I say some of the bad effects of acid rain? Um, yeah, because acid rain has many bad effects. So, changes soil pH and kills trees would be one. And then changes the pH of water and kills fish, damages buildings that are made of limestone or constructions made of limestone. But sulfur dioxide probably also causes respiratory illness. So it depends whether they want acid rain, respiratory illness, or whether I give two effects of acid rain. As it says, give two problems caused by it as an atmospheric pollutant. I'm going to give the two problems of acid rain. So I'm going to say um, acid rain lowers pH of soil, killing trees, or I'm going to say acid rage, acid rage, acid rain lowers pH of water, killing fish. They might say, you're just talking about killing organisms. That's the same thing. So I could also say acid rain damages limestone buildings. Well, really, buildings, gravestones, anything made of limestone, statues. So it damages those as well. So, but these are all problems with acid rain. If I want to talk about something else, I might be able to say respiratory issues. Okay, so if on the mark scheme they're like, nah, too much talking about acid rain, mate, then I will bust out respiratory issues, breathing problems. Okay, let's give myself 2 marks for that and a pat on the back. Well done. Oh, I'm tired. 3.4, describe how carbon monoxide can be produced by transport. So, carbon monoxide as the formula, CO. Pause the video, explain how it's produced. Okay, I'm going to go through how it's produced. You've got it's made by something called incomplete combustion. So it is made from incomplete burning or combustion, as is the funky term. And what does that mean, incomplete combustion? When there is not enough oxygen. So when there's not enough oxygen, we do incomplete combustion. Let me just give you a quick rundown, right? Here's some complete combustion. This is the lovely methane. That is what you have in your Bunsen burners and in cow farts. And if you join methane with oxygen, we're going to make carbon dioxide and water. That is complete combustion. And balance that up. I've got 4 H's there, so I'm going to put a 2 there. Bosh. Got 1 carbon there, so I can leave that there. That's 2 oxygens and 2 oxygens there, so I need a big 2 there. So that would be complete combustion. Incomplete combustion is there's not enough oxygen to form all of this. So instead, what we get is carbon monoxide plus H2O. I'd actually need to balance that up because the hydrogens aren't balanced. So I get 2 oxygens there and 1 there. So this would be 1.5. Instead of 2 oxygens like we needed to get carbon dioxide, if there's only 1.5 oxygens knocking about as a ratio of oxygen to methane, then we're going to make carbon monoxide instead. Okay, and that is incomplete combustion when there's not enough oxygen. All right, you get the idea. The stupid voices are optional. 3.5 catalytic converters are fitted to car exhaust to reduce the amount of pollution from cars. Carbon monoxide and nitrogen dioxide react in a catalytic converter. Nitrogen and carbon dioxide are produced. Write a balanced equation for the reaction. So you're going to get this somewhere in chemistry, okay, where they're going to give you some words and ask you to write an equation from it. And they're going to give us the names. We just need to put the formulas down and then 1 mark for balancing. So carbon monoxide and nitrogen dioxide react. The reactants are over here. Carbon monoxide, well, that's the formula for carbon monoxide. And they've given us the formula for the nitrogen dioxide. Okay, so they gave us the reactants. It's in the words. Nitrogen and carbon dioxide are produced. You all know the formula of carbon dioxide. If you don't, slap yourself in the head 3 times. Don't know if that was 3 or 4. And then nitrogen, you should know the formula. Um, have no fear of ice cold bread or beer, whatever you want to say. Nitrogen is a diatomic molecule. It has the elemental symbol N, but like quite a few non-metals, all of the halogens, hydrogen and oxygen, it has a little 2 after it. So this would get you 1 mark for getting the formulas right. The second mark is for balancing. So I've only got 2 oxygens here and I've got 1, 2, 3 here. So I have an issue. I've got 3 over here and 2 here. I want to make an even number of oxygens, and I'm going to do that by putting a 2 there. That's going to give me 2 carbons, but it's going to give me 2 oxygens and 2 there. And then if I put a 2 here, oh my gosh, the balancing is hard here, peoples. So we can see that I've only got 1 nitrogen. I definitely need a 2 here. So we're going to have to go back and forth, back and forth. Right, 2NO2, that makes 4 oxygen. Right, let's get rid of this and this. These are going to have to change. So I'm going to leave that there. That is perfect. I've got 2 ends there. I should have started there with the 2 there. That makes 2 ends there. Now in total, I've got 5 oxygen here and I've only got 2 here. So I need to make this even. So I'm going to put a 2 there. That makes 2 oxygens there. And that makes 2 oxygens there. That is 4 oxygen. Oh no, that is 6 oxygens. So that means I've got to put a 3 there. This is getting harder and harder and harder and harder. And let's put a 3. That makes 6 oxygens. What if that makes 6 oxygens? I'd have to put a 3 there though. Which would make 7. This is very difficult for my simple little shooty brain. Oh my God, you could just take the 1 mark right now, but I would just keep working up because if I do that, 3 times 2 is 6. 3 times that is 3, and 2 times that is 4. That's 7. So we're still not balanced. I don't want to F around with the nitrogen dioxide or the nitrogen because I don't want to change that because I've got 2 ends there and 2 ends there. They're happy. I want to leave them and just mess around with these bad boys. Right, let me go to 4 and see what happens if I put a 4 there. And let's put a 4 here. So I'm just working my way up in a real crusty way. Oh my days. Right, let's try this now. 4 carbons, 4 carbons. We're happy. 4 times O2 is 8 O's here. That looks like 80. That's not what I mean. That's 8 O's. And then over here, I've got 2 times O2 is 4 O's. And 4 times O, I've got 8 O's here. Finally, the rock. No, finally, yes, we are here. Good. 8 O's, 8 O's. Let's just check the nitrogen again. 2 N's, 2 N's. Beautiful. 4 C's, 4 C's. 8 O's, 8 O's. Oh my gosh, that was long. Don't know why I found that hard today, but there we go. It happens. Question 4. Printer ink is a mixture of chemicals. The student used chromatography to investigate the colors in a printer ink. The student put a spot of printer ink on the start line. Let's shrink this so we can actually see the question, Tom. So there's the printer ink. That's the start line. And the results are as follows. We get left with red, yellow, and blue. And then we have something called the solvent front. Let's check it out. Explain why the red color did not move from the start line. So obviously the printer ink was originally made of all three colors, all there, but the red color hasn't moved off the starter line. What does that mean? Well, let's see what the solvent was. It doesn't tell us what the solvent is. So, but we can say um, the red color or ink is not soluble in the solvent. So that's why it didn't move, because it doesn't dissolve in the solvent. It has a very low affinity for the mobile phase, and that is 2 marks. Let's boom on to 4.2. The blue color moves 6.4 centimeters up the chromatogram. The RF value of the blue color is 0.87. Calculate the distance moved by the solvent. Give your answer to two significant figures, and that is 4 marks. Right, 6.4 and 0.87. So what color were they on about? The blue? The bluesy blue? Yeah, blue color. So what they're doing, I'm going to do this up here. Let me swing down. Why don't you have a go at this question? Grab your calculator, grab a piece of paper, bash this question out, and then I'll go for it. Right, I'm going to explain it for you. So what happens is the solvent moves 100% of the way up the paper. The blue moved 6.4 centimeters. The RF value is the ratio of how far the blue moved compared to the solvent. And we write the equation like this. RF value, the retention factor it actually stands for, but I like to think of it as a ratio, is the distance moved by the dye or the ink. So it's the distance moved by dye or ink, and that is over distance moved by solvent. Now, the solvent is always going to be 100%, so whatever that is. We want to find out how far did the solvent move. Well, the RF value is the ratio of how far the dye moved compared to the solvent. So it's going to be like, if this was to scale, which it says not to scale, that would be about 7 centimeters, the solvent. But we're going to find it out because the RF value was 0.87. The distance moved by the dye is 6.4. So we have 0.87 is equal to 6.4 dissolved by the distance of the solvent. I want to rearrange this. So what I'm going to do is 6.4 divided by 0.87, and I'm going to get that because if I put that into a triangle, whatever's at the top of the dividing line goes to the top of my triangle. So I'm going to have 6.4 over 0.87, and at the other bottom, I've got my unknown. So let me smash that in the cal. Oh my days, where's my calculator? There it is. Found it. Right. So I'm going to go 6.4 divided by 0.87, and the answer is 7.35. So this equals the solvent front, how far the water moved up the paper, is 7.356321. Right, I don't need the rest of this, but you get the idea. Now it's 4 marks. They want me to two significant figures. So, was it two or three? If it was three significant figures, I'd be going to 7.36 because that is bigger, but we're going to just two figures. Now, as we have a 5 next to the 3, we're going to push that up. The answer is going to be 7.4, and that is two significant figures. Why did I raise it? Because it's 7.3, but then the next number, if it's 5 or bigger, you push that up. So it becomes 7.4, and that will get us 4 fat marks. Oh. There were 4 colors in the printer ink. Suggest one reason why only 3 colors were visible on the chromatogram. Now, suggest means any sensible reason. So suggest one reason why only 3 colors were visible on the chromatogram. So maybe the fourth color is white, so does not show up, right? But more than likely, if I go back to the diagram, well, uh, okay, more than likely, like we had the red color at the bottom, which didn't move. Maybe there's a lighter color in there, like pink or orange, that's hidden behind that red color. So we might say it might have been insoluble and hidden by the red. Or another reason, another reason might be that it had the same RF value, like 0.87, as the blue or yellow, but is a lighter color, so is hidden. Okay, you get the idea, peeps. That was the suggestion. Suggest how the student could use the chromatography to show there were four colors in the printer ink. Suggest how the student could use chromatography, not the chromatography, to show there were four colors in the printer ink. Well, what we could actually do is use a different solvent. So use a different solvent. So just because the red color is insoluble and doesn't move in, say, water, maybe that red color will move if we put it in an alcohol like ethanol, or in like nail varnish remover like propanone, if we use a ketone or something like that. If we use a different solvent, maybe some of those other colors will move different distances and we'll start to see them. Okay. Wunderbar. Let's go. So that's a little suggest. The suggest there was basically that there are other colors hidden behind these spots and they're lighter than these spots, so you can't see them. Okay. We're on question 5. Sulfuric acid is produced by an industrial process. In the process, sulfur dioxide reacts with oxygen to produce sulfur trioxide. The equation for the reversible reaction is 2SO2 plus O2 goes to 2SO3. The Ford reaction releases 190 kilojoules of energy. So it's released, which means negative. It's taken away from the system, minus 198. What is the amount of energy transferred during the reverse reaction? Pause the video, have a go. So it's going to be, in the reverse reaction, it's going to be plus 198. Now they've made that really difficult. So it is going to be this means less than 198 equals 198 or 198. It's basically going to be 198. You don't need to worry about the minus and plus. If 198 comes out that way, 198 goes that way, but 198 is released that way, 198 goes in that way. But so they're talking about the amount of energy transfer, which means we don't have to worry about the plus or minus. If they'd said how much energy was released during the reverse reaction, it would be plus 198. Okay, anywho, yeah, that was confusing. I could definitely see people getting that wrong. 5.2, the concentration of oxygen is increased. What is the effect on the position of equilibrium? Well, oxygen is on the reactant side. Le Chatelier said, whatever you do to the equation, it will do the opposite. So here's reaction, here's product. If we add more oxygen, the reaction will quickly move this way to get rid of the oxygen. So we will get more sulfur trioxide, we'll get a higher yield. Yield means more product. So we're going to, what is the effect? Oh, the position of equilibrium is going to shift to the right, which is where the product is, to try and get rid of the extra oxygen you've put in. Let's go, let's go, let's go, let's go. The pressure is decreased. What is the effect on the position of equilibrium? Why don't you pause the video, have a go? Okay, what I'm going to do is I'm going to zing up and we're going to have a little look. So when we're talking about pressure, it's talking about gas molecules. How many G's are over here? Well, I've got 2 times G, that's 2 G's, plus another G over here. There's 3 G's, 3 gas molecules on this side of the equation. On this side of the equation, there are only 2 G's, 2 gas molecules. Now, if you increase the pressure, Le Chatelier says it will go to the side to oppose that. So the more gas molecules, the higher the pressure. So if you put a high pressure on this, it's going to shift to the right to get rid of the high pressure. If you decrease the pressure, then it's going to move to the side with the most gas molecules to try and increase the pressure. The reaction always does the opposite of what you do. So let's have a look. What was the questione? The concentration, I know. The pressure is decreased. So which side is it going to go to? Well, the reaction is going to shift this way to try and make more gas molecules and increase the pressure again. So it does the opposite of what you do. So the equilibrium shifts to the left. Okay, as that's the side with the most gas molecules, if you decrease the pressure. The temperatures are increased. What is the effect on the position of equilibrium? So we're going to go up now. God, they're really getting equilibriesque. It tells us that this reaction, check it out. This reaction releases 198 of energy. So this is exothermic. Exo means energy out. So if I increase the temperature, it's going to go away from the side that releases energy, and it's going to try and bring the temperature down by absorbing the energy. So it's going to go to the endo side if I increase the temperature. If you increase the temperature of an exothermic reaction, it shifts to the left. What did they do? Okay, if we increase the temperature, it's going to shift to the left to the cold or endothermic side to try and decrease the temperature. It's going to try and do the opposite. That's what Le Chatelier said. So that's a hot reaction, an exothermic reaction. Right, 5.5, a catalyst is used in the reaction to suggest what the effect of the catalyst is on the equilibrium position. So the effect, none. Catalysts speed up the rate of reaction. They do not affect the equilibrium position. So they speed up the rate of both the forward and backward reaction the same amount. So if the forward reaction is going at 1 mole per second, they speed up the backward reaction to 1 mole a second as well. So the reaction does not change its equilibrium position. Both the forward and backward speed up by the exact same amount. They do, however, increase the speed that you get to equilibrium, but they do not change the position of equilibrium. Bosh. We're on to the final question, which is just about, because I've been waffling far too long. Oh, no, we're not. A scientist measured how the number of moles of sulfur dioxide, oxygen, and sulfur trioxide varied with time during the reaction. Figure 5 shows the results, number of moles, time in seconds. So we can see the number of moles of oxygen and sulfur dioxide decreased and the number of sulfur trioxide increased, but all of them got to a position where they no longer change. So let's have a look at the questiones. Determine the time taken for the reaction to reach equilibrium. 3 marks, explain your answer. Equilibrium is when the amount of product and reactants do not change. So where did that happen? All we need to do here, folks, is find the bit where it goes straight. And it's right there. So it's taken, now I need to work out what is this scale. Well, we got 50 and we've got 10 squares. So I'm going to do 50 divided by 10. Each square equals 5. So now I know my scale. That's 205, 210. So it took 210 seconds until there was no change in the amounts of substance. And that means you've reached equilibrium, equal amounts of each substance. 210 seconds to reach equilibrium. How do we know they're there? The line has gone straight. The amount of product, this is the product, sulfur trioxide, and reactants does not change. Okay, let's go put that into words. So we're going with 210 seconds. Oh, what is this? Explanation. Um, oh my days. The lines for products and reactants are level and do not change. The amount of product and reactant stay the same. So that is the explanation of how we got to our answer. And it's because the forward and backward reaction are happening at the same rate, whatever. Right. Question 5.7. This question is like goes on and on and on and on. Figure 6 shows the results of sulfur for sulfur trioxide. Number of moles of sulfur trioxide, time in seconds. Okay. What do you want? Determine the rate of reaction at 60 seconds. So they want us to determine the rate of reaction at 60 seconds on this graph. We're going to have to do a tangent, folks. What we're going to do, we're going to go to 60 seconds and each one of these, again, 50 divided by 10, like in the last graph. So it's 5 seconds. So 60 seconds is here. No, that is Crustaluli. Let's go a bit closer. There is the second line past the 50. That is 60 seconds. We can see there that we're going to do a dot. Now, this is a curve. So what I'm going to have to do here is do a tan. Oh, I don't even know if I need a tangent here, to be honest. Maybe I don't actually need a tangent. It's not much of a curve. But when you draw a tangent, it should roughly be visually the same on each side. So that is rubbish and would not do. The space between the dot and the line should be the same on each side. If this is almost straight, I don't really need a tangent. So um, this is actually really hard to do on this. Can I move that up there? No, I can't. Basically, I want all my days. That doesn't look good. Yeah, that doesn't look very good. That's the crustiest tangent I've ever drawn in my life. Right, what I'm going to do here is then just go like that and like that. And then I just want to do y over x like that, folks. Y divided by x. I mean, it probably is going to work out the same as if I just said 4 over 60. Because it's almost a straight line, so it's probably just going to work out the same, but I'm going to do it this way. So I've got 50 as x, and then what am I going to put for y? Y is a little bit harder, so we've got 2 here, and then I've got 2 more squares. What is each square here? Well, I've got 2. The value is 2, and I'm dividing it by 10. So each square is, what's that, 0.2? Yeah, 0.2. So this is 2.2. So I'm doing 2.2 over 50, and that is my rate of reaction. So 2.2 divided by 50 equals 0.044, and that is moles per seconds. That would be my rate of reaction at 60 seconds. Now, I can't remember how many decimal places they asked for. I'm going to zing down and check it out, folks. And let me just see. If I didn't do a tangent and I just did 4 divided by 60, what would that equal? 4 divided by 60 would equal 0.0667. So I'm glad I did a tangent because we get a different result. Let's go. Yep, we've done that. Okay. Question 6. The Earth's natural resources are used to manufacture useful products. One useful product is potable water. Potable water can be produced from sea by distillation. Give one disadvantage of using distillation to produce potable water. It uses heat energy because you need to boil the water and evaporate the water to get it away from the impurities. So it uses heat energy. It costs money. Okay, there we go. Right, bosh. 6.2, describe one other method to produce potable water from seawater. So this is gonna be, so you could use distillation, which is done in like a salination plant, but we could use reverse osmosis. And reverse osmosis uses a semi-impermeable membrane. The only difference is it moves um, it moves water against the concentration gradient using energy and a permeable membrane. And that is reverse osmosis. Okay. A student investigated the mass of dissolved solids in 100 centimeter cubes of seawater. The method used: weigh an evaporating basin, measure 100 centimeter cubed of seawater, pour the seawater into an evaporating basin, heat the evaporating basin, weigh the evaporating basin and contents, calculate the mass of dissolved solids in the seawater. Explain how repeating steps 4 and 5 would improve this method. So how would heat the evaporating basin, weigh the evaporating basin and contents. Right, we want to, this investigation was designed, a student investigated the mass of solids in 100 centimeter of seawater. Basically, they've tried to evaporate the water and then weigh it again and find out how much solid is in there. Here's the problem. They heated the basin and then weighed it. And it's, how do they know they've got rid of all the water? So what they should have done is um, heat until all the water has evaporated. Uh, Basically, they would know all the water had evaporated. Okay, so they need to heat it until all the water's evaporated. Once the mass does not change, I should be heat until mass does not change. So I needed to put that, I reckon, as well, because my other 2 points are the same. So I needed to say heat until the mass does not change. This has proved all the water has evaporated. And then you would know you're only left with solids. The total mass in dissolved solids is 3.5. The percentage of sodium chloride in the dissolved solid is 77.8. Calculate the mass of sodium chloride dissolved in 100 centimeters. So we just need to do 77.8 of 3.5. And what you do there is you go 7.8. You divide it by 100, and that's going to give you 0.778. And you times that by 3.5. And that's going to get your answer 0.778 times 3.5, and that is going to get us bosh 2.723 grams. You could round that to 27, you could round that to 272. Okay, that's going to get you 2 fat marks. Okay, so we're on 6.5. We're nearly there, folks. Make sure that you hit the like, you subscribe to the channel, massively helps out all that business. Biological methods are used to extract metal compounds from metal ores. 6.5, one method of producing copper from a low-grade copper ore is by using bacteria. The bacteria produce leachate solutions that contain copper compounds. Give 2 methods that can be used to extract copper from these leachate solutions. Why don't you pause the video, have a go, and then I'll go through the answers. Right. So what the hell is this about? Well, in the world, we have low-grade copper ores. These are rocks without a lot of copper metal in. And normally, by normal mining standards, we don't bother breaking them up and trying to get the copper out because it's too expensive and you don't get enough copper. But if we want to keep copper sustainable for future generations, we've got to use low-grade copper ores as a way to get the copper out. And we can do this by taking the rock, which has the copper inside it. So imagine this is a rock. It looks like a potato, but never mind. We can then get some bacteria to live on the rock. And what the bacteria do is they take the copper out of the rock into their body and they produce a liquid called a leachate. And this liquid that they produce contains the copper metals inside it, or the metal ions, of which we're interested in the copper inside it. And what this question is saying, give 2 methods that can be used to get the copper from the leachate. The leachate is this here, made by the bacteria that live on the rock. So how can we get it out? Well, we need to extract the copper, and we can do that by displacement with scrap iron. So we can displace the copper using scrap iron. Now, do you have to say scrap iron? No. Any metal that is more reactive, but in theory, it's better to use some cheap old iron that you don't need anymore. Iron is higher up in the reactivity series than copper, and it will join with the other elements of the solution and push the copper out. And so you'll get the pure copper. The other method is by doing that dreaded substance electrolysis, which separates different ions and turns them back into elements. So if you do electrolysis on the leachate solution, you'll get copper metal formed at one of the electrodes. Okie dokie. Let's zing this in. Right. Phytomining uses plants to absorb metal compounds from low-grade ores. 6.6, describe how metal compounds are obtained from plants. So this is another chance for you to pause the video and have a go. Phytomining uses plants to get metal from low-grade ore. So very similar to the using the bacteria, bioleaching. Phytomining is slightly different. So pause the video, see if you can write down 3 ways that we can get the metal compounds from the plants. I'm going to go through it now. So here we go. Right. Imagine you got the rock. Once again, the rock has copper in it. It's an ore, which is a rock, but low grade means it doesn't have a lot of copper. What we can do as an option is grow some sort of plant on the rock. Okay, and what is that plant going to do? It's going to suck that copper. Look at my incredible art skills, level 4 GCSE peeps. Right, it's going to suck that copper up into its leaves and into its body like so. And all we need to then do is set fire to the plant. I know, pretty grim. What's the plant ever done to us? But we burn the plant, okay? Take it and we burn that plant. And what is left behind after you burn something? Well, you have ash, black ash or grey ash, whatever. And in that ash is bits of copper. So how are we going to get the copper out of the ash? Well, we take the ash and we dissolve it in a solution, basically mix with water and dissolve it into a solution. And we're now at that stage we were with the bacteria leachate, where we have bits of copper inside the solution, and our choices are at this point to do electrolysis or displacement with scrap iron to remove it. I need to put this into words. So describe how metal compounds are obtained by plants. So we say grow plant on the ore. The plant absorbs, absorbs, I don't know what that means, absorbs the copper ions in the roots. So it's going to get the copper ions in the roots. We're then going to burn the plant. Okay. They've already said this, so I'm not going to get any marks for that, but uses plants to absorb metal compounds. Yeah, I'm not even going to get anything for that, but I am going to say burn the plant. Woo! That gets me a mark. The ash contains copper ions. Cu is the elemental symbol. So I'm going to say make a solution of ash. So we're going to make a solution of the ash. So it's very similar to the leachate. And now we're going to extract with electrolysis or displacement. And again, the displacement is with the scrap iron. So essentially, you're going to burn the plant to form an ash, dissolve it in water to make a solution, and then extract with electrolysis or displacement. Okay. Oh, damn this hay fever. Let's move on. 6.7. Oh, we're here, folks. We're at the end. I could cry. 6.7, nickel is produced by phytomining. 1 hectare of plants produces 215 kilograms of nickel. Determine the area required to produce 750 kilograms of nickel. Give your answer in meters squared. 1 hectare equals 10,000 meters squared. It's worth 3 marks. It's a mental maths question, and you have 10% of your science exams, whether it's chemistry, physics, or biology, have to be maths calculations, minimum 10%. So, 250 kilograms of nickel. How many lots or that's 1 hectare makes, so 1H equals 215 kilograms. So how many H's, how many hectares can we do with 750 kilograms? So I'm going to do 750 divided by 15 kilograms, and this is going to give me the total number of hectares we have. Let's check it out. So we go 750 divided by 215. That is going to give us 3.48 hectares. 3.488. I could round that if I want. I'm going to call that 3.49 hectares, right? Um, Now we want to know, how big is the area in meters? Well, there's 10,000 meters in a hectare and we have 3.49. So we're going to go 3.49 times 10,000. You could keep it as 3.488. It's up to you. And that is going to be times 10,000 equals 34,000. So if you didn't round it up, you get 34,800 and 83 meters squared, or you could just round it up. Hopefully they take a rounded number. Otherwise, I'm screwed. So 1 mark for dividing 750 by 215, 1 mark for timesing that by 10,000, and 1 mark for your answer. That's the end. Don't forget, sharing's caring. Hit the like, punch up the bell, subscribe. Let's get to the marks. Let's smash those GCSEs.
You're still here? It's over.